I'm actually so relieved to see so many folks in the room. About 10 years ago, I was giving a talk, and at the same time, Larry Wall was giving a talk on Perl 6, which also kind of dates it. And when I looked in the schedule and I saw Rust in production at the same time slot, it's like, oh, fuck, not again. That talk had, 10 years ago, had one person in attendance, and he was still on his laptop the whole time, kind of not making eye contact. So anyway, glad to see so many folks here. I'm Adam Leventhal. I was asked to attend this talk, attend this conference late last week. I want to start with a graph. There are a bunch of graphs in this session, most generated, a couple in Excel, and my apologies for this. This one I didn't actually make. Most of the other graphs are going to pertain to performance data, time, latency, and so forth. This one comes from a study that I was reading recently by a grad student in psychology at the University of Kansas. She was walking around to bars in Kansas City and evaluating people's acceptance of hierarchy versus egalitarianism, and comparing that to what they blew on a breathalyzer. So this is basically how much you value egalitarianism and how drunk you are. And she saw this great correlation, right, of the drunker you get, the less interested you are in egalitarianism. Egalitarianism is kind of a higher order function that you need to think about to get right. So that could be one conclusion. Or you think maybe just people who really like hierarchy are just drunkards. It's like drunk for Trump kind of t-shirts walking around. But no, they also did a study evaluating distraction. So if you're doing a complicated task, they seem the same kind of result. So what's my point here? So when I was asked late last week to put a presentation together for today, much like not kind of having a little alcohol in a system, my default is to go to two topics I know well, dtrace and OpenZFS. So this is not to say I'm drunk right now giving the talk, merely that I was under a little time pressure. Okay, I might be in the wrong room, but just want to make sure. OpenZFS, has anyone heard of it? Has anyone used it? Okay, a couple of hands. So this is a file system that Sun developed and has now been an open source project for going on 10 years. And now, so I started my career at Sun, worked on dtrace and ZFS. I'll get into the details of some of those. And then was, until recently, CTO of Delphix, which was a company that did a bunch of work around ZFS and data. So for you in the room, and again, I'm hoping I get the audience right, my guess is some of you are the folks who, when your organization's engine explodes, you're the one that needs to go crawl onto the wing and fix it because they won't land the plane. Or maybe you're kind of dtrace curious, like some of your friends have been into dtrace. You've kind of wondered what it's about and want to see for yourself. So I wanted to kind of talk about dtrace, but motivated through a particular customer encounter I had a few years ago. So I'm going to talk a little bit about what dtrace is, and then also a little bit about the customer. But I'm going to start with the customer. So this was an important customer for my company. At the time, it was our biggest deal in history, and they started having horrible, debilitating performance problems nearly immediately. And we kind of screwed up the analysis. I'm sure you guys have been in these types of situations before where you get the kind of cargo cult or IT administrator. Like one time I saw this problem and then I did this and the problem went away. And so we did that with the customer for about 6 months, kind of reconfigure that way, reconfigure this way, until they were just fed up. And then our CEO needed to fly out and say they were sorry, and there was lots of frustration, but nothing was getting fixed. So finally, I went to the customer. Customer was late for the meeting. I already knew that this was not going to be a great meeting. Usually when you're meeting with customers who have had a really bad time. So customer's late, and before sitting down, he says this: ZFS is a piece of shit. You could not have made a worse choice. So in that moment, a lot of thoughts occurred to me, but I quickly formulated a plan. My plan was this. I was going to use dtrace. I was going to figure out every one of their problems. Then I was going to fix all of their problems. And then I was going to be super magnanimous to annoy the shit out of them. So that was the plan that I came up with in a moment of bravado. So So what is dtrace? So in order to diagnose problems, you need data. And dtrace is a system for collecting data about your system. It's a dynamic instrumentation framework. We first built it, we started building it in 2001, finished it in 2003, and open sourced it in 2004. First on the Solaris operating system, and it's since been ported to Mac OS X, FreeBSD, Linux. It's on the PlayStation Vita. It's actually on iOS, but only when they show it to me in the darkened corners of rooms. I don't know why they don't let everyone use it. It's designed for production use, and as I mentioned before, it's systemic in scope. A gentleman came up to me beforehand and said, what language are you going to be focusing on? And I was like, what language? He's like, the system you're debugging. And the great thing about dtrace is it's, again, designed for systemic scope. It's not a Java tool for Java, or a C tool for C, or a kernel tool for the kernel, or a debugger tool for a debugger, or for a developer. It's really designed to go across your entire system to understand the interactions. And as we know, applications are no longer like a single binary or even a single process, but these sprawling concepts. It is, however, a single system, so dtrace is lagging behind in that it's not one of these tools for doing broad analysis, but we'll go into that in a little detail. All right, so what I wanted to do is now actually show you dtrace, and I'm gonna do that from my terminal here. Great. Folks in the back of the room, yes, no? Okay, good. Good enough font size. So this is also a great opportunity. I know there are a bunch of folks with Mac laptops. At this point, I would certainly not be offended if you wanted to pop open your laptop and kind of do a work-along thing. They ported dtrace to Mac OS X in about 2005, and it was totally by surprise to us. As you know, Apple doesn't kind of tell anyone what they're doing until it's basically already done. I had this meeting with the Apple folks where they said, oh, we're evaluating porting dtrace to Mac OS X. So no, that's great. They asked us the most picayune details, and dummies that we were like, wow, those guys have really done a lot of research. They hadn't done a lot of research. They had basically finished the port. They were like one question away from getting the thing done. WWDC was the next week, and they shipped it. Like, oh, we're dumb. Okay. So first thing to do is be root. So sudo bash is what I like to do, or you can do sudo dtrace. So dtrace is like a normal Unix command line utility. You type it, and it gives you some inscrutable output about how to use it. So you can ignore all that. So the first thing we're going to do is do dtrace -l. That's going to list all the probes on this system. On this Mac, my little laptop here, there are about 400,000 probes. So 400,000 points of discrete instrumentation where I can go modify the system, record some information, or get some timing results, or whatever. So 400,000 points of instrumentation, which is kind of a lot. One of the biggest challenges for people starting with dtrace is that kind of where to start. With, I'm not going to just turn on all 400,000 probes. It's not going to perform so well. So usually you start from things that you understand pretty well. And I kind of grew up as a kernel guy. So as a kernel guy, all userland applications basically look like system call load generators. So that's kind of where I tend to start. So with dtrace, you can specify your probe with this for tuple of provider, module, function, and name. I'm going to do minus syscall. I'm going to do this. So this lists a bunch of probes on the system. These are all the system call probes. So in this case, the provider is syscall, the module is unspecified, the function is microstack shot. I've never seen that one before. I don't know what that could possibly do. I guess I can man it. And then there's an entry and return probe. Okay, so for tuple, provider module, function and name uniquely identifies every point of instrumentation on the system. I can list them with the -n, and if I omit that -l option, it will enable all these probes. It'll take your system from being fully optimized to something where it's now been modified to record information. So I can do this, and lots of system calls are happening, so it'll start spewing output. But that's not super interesting. It takes a little while to control C. But I can also program it to record data dynamically. Folks have probably used static tracing tools where you can turn on probes, and it'll give you the information that the author of that probe anticipated that you might need. But you've also probably been in the situation where you say, well, if I had one more piece of data, yes, you told me the process ID, but if you told me the thread ID, that'd be great. Or if you gave me the stack trace, that'd be great. dtrace lets you program these probes to give you the information that you need at those points of instrumentation. So in this case, I'm interested in the name of the binary that is invoking the system call. So I do that by adding this trace exec name. And now it's going to spew a bunch of output at me, which again is not exactly what I want. Now I could take this, pipe it into Perl 6, or maybe Rust, and figure out kind of my answer. But one of the key properties of dtrace is that we want to give you concise answers to your potentially complex, to your arbitrary questions. So there's a very powerful primitive of dtrace called aggregations. Okay, so here I'm going to use an aggregation. Oh, and I'm going to change my system calls, if I can get my keys right. All right. So now what I'm going to do is light up all 500 entry probes for system calls to figure out what application on my computer is generating the most system calls. Now, back in the Stone Age when I used to work on a server, I needed to generate load, but fortunately, this is like my Mac, and it's got whirling icons and all kinds of crap happening without me touching it. So all I need to do is pontificate for a few minutes, and I'll get lots of load generated on the system. So these are all the applications that have been generating, that have been invoking system calls, and every time I do this demo, I kind of find something new. I've always kind of wondered why Google Talk plugin is like what it's doing when I'm not actually using Google Talk. Maybe I don't want to know. So I can dive into that now. So let's see. Oh, a word of warning for folks who are actually trying to follow along. Apple did something kind of weird in the last version of the operating system. I can't remember what version it was. Not Yosemite, the one after that. No, whatever. Where they enabled some sort of security feature called SIP, which kind of castrates dtrace in certain circumstances. So if you get some errors that I don't, you can Google up SIP and dtrace, and it'll tell you how to take away that particular form of castration. I wish I had used a different metaphor now. So what I can do is now dive into this particular process, the Google Talk plugin, and now I want to know not just that it is invoking system calls, but which system calls it's invoking. I can do that with probe func. As I mentioned, each probe is provider, module, function, and name. Those are also variables that I can trace to understand which probe it is that is firing. I hit Control C, and man, that's super boring. Let's find a different one. It turns out Google Talk plugin is like just asking what time it is. What time is it? What time is it? What time is it? Like, do you have somewhere to be? All right, let's try someone different. If someone falls in love with one of these, feel free to holler. Otherwise, I'm going to pick one. All right, good. Let's go back to this. All right. So let's see what TweetDeck is doing. It'll probably be also asking what time it is, given my luck. All right, do this. Maybe we'll actually go to TweetDeck and give it a chance. All right, you see the weird stuff I follow. And there it is. Okay, so now we've got a bunch of information about what TweetDeck was doing at that particular time. And now we can start to dig in deeper. Like, I'm kind of surprised that it's doing these stats. So stat is when you're checking for a particular file in the file system. I'm surprised it's looking at all. So let's go now focus on that specific probe. And now we can look at the stack trace of where we are in TweetDeck when that's happening. So here I'm using ustack. And maybe let's go back and we'll generate some load by scrolling. There we go. And hit Control C. Now I've got a stack trace of where we are in TweetDeck as it's executing a bunch of these system calls. So while we're not TweetDeck developers, it allows us, I just want to back up for a second, because what we've done is gone from a systemic level activity that we might have been seeing, the number of system calls, and then drive it to a particular application and potentially even a particular line of code where we see that coming from. Okay. One other thing, while I've got TweetDeck up on the table, TweetDeck is, I want to take a look at user level process tracing. So we were kernel guys when we were writing this thing, so we started focusing on things like kernel functions and system calls, but very quickly branched out into userland functions and then to dynamic languages like Java and Python and Node and other places like that. So you can instrument all different parts of your system. So in this case, I'm going to dive into user-level process tracing on TweetDeck. So I'm going to dtrace -n, PID, and then the name of the process. And I'm going to see if it's doing any allocations. Tree. Let's see if it's mallocing. Really? That's super surprising. Okay, good. And then, so I'm going to do a bunch of allocations. Now I'm going to use a different kind of aggregation called quantize. And this is kind of important. We're going to be using this a bunch. So the first argument, arg0 to the malloc function, is the number of bytes I want to allocate. So I'm going to do this, generate some load, hit Control-C. And now what I've got, I'm going to, in the back of the room, tell me if you stop being able to see this now. What I've got here is a gorgeous ASCII art diagram with power of 2 buckets that shows the distribution of sizes of allocations. Okay, so this is for malloc, for TweetDeck, how the size of the different allocations it's making. We can see it's doing 44 0-byte allocations, a bunch of 2-byte allocations, some all the way up at 65K. Folks with me understand what this picture means? Okay, I got a couple of thumbs up. That's great. Thank you. So I can collect data that can be of statistical nature and to understand it. Now I also want to show one more example before I get back to the customer example that I'm going to focus on. So I'm going to go into vartemp and write a new D script, d.d. So in addition to be able to executing all this stuff at the command line, I can also do it in a script. Let's see, what was the name of that process again? Okay, this guy. TweetDeck, all right. So user sbin dtrace -s, so that says I'm going to do a script. Now what I'm going to do is say every time I do a write syscall, I'm going to set a little thread local variable to timestamp. So what I've done right here is I've programmed every time I enter a new write, every time I'm writing, doing a file system write, for example, I'm going to record a timestamp in a thread local variable. Self points to TS, means thread local. TS is a name I made up. Timestamp is a nanosecond timestamp. And then I'm going to say when I return from write, and I had previously entered, then what I'll do is I will quantize based on timestamp minus self points to TS. And then self points to TS back to 0. Okay, so what this is going to do is measure how long it takes to do writes on this system. And I'll run this guy, it'll light up a couple of probes, I'll hope that somebody's doing some writes, and I hit Control-C. Okay, so now I get a distribution now of latency, nanosecond latency for how long writes took. And we can see that a lot of writes took only 4 microseconds, all the way up to 32 microseconds. Kind of surprising to me, but I guess this SSD in the new laptop is pretty snappy, or there are not that many writes, maybe it's just hitting memory or something. Okay. So that's kind of the very basics of dtrace and kind of how it works. I'm going to go into some deeper examples. Any questions off the bat, or any things that people maybe saw on the screen that weren't clear on, or wanted me to double click on a little more? All right, I'm kind of please.
What's the system impact of if you just wanted to run this? Could you run it on a production system?
Yeah, so the question is. Does this work on a production system? Let me talk about that because that's super important. So dtrace is meant to be safe for use in production. It is intended for production systems. When dtrace is not in use, there is 0 performance overhead. And yet all of those probes are available. As soon as you start tracing, as soon as you enable probes, and as soon as you've modified the system to record some information, you are going to pay a penalty, right? You can't change a system to have it do more without there being some cost. However, that cost is proportional to the question that you ask. if you, I've seen some sort of naive uses of dtrace that are like, why don't you just enable the, turn on dtrace for every function in a process, dump it to a log, and I'll go look through it later or whatever. That's incredibly painful. If I'm looking at events that are on the order of tens of thousands or hundreds of thousands of times per second, that's not so bad. Also keep in mind that typically these systems that you're looking at are already in some amount of pain. And to cause a little more pain to be able to understand the pathologies is typically worthwhile. But again, the high level is there's no cost when disabled, and the cost of using dtrace, the cost of understanding what the system is doing, is proportional to the type of question that you're asking. But it is always safe. So dtrace will never cause pathological performance disruption. It'll notice if it's using up a bunch of CPU time and disable itself. So it'll turn itself off and say, sorry, I think I was hurting the system too badly. It will also never put you in a situation where it could corrupt memory or corrupt data. Yes, sir, another question.
So would that lead to possibly missing an event?
So the question is, could it lead to missing an event? Yeah, so if slowing down a system, even by a tenth of a percent or 10%, could cause you to miss an event, yes. But I think only in the same way that additional load on the system could cause the system to misbehave. So in the same way that if I SSH to a box and I did a untar or whatever, that would cause potentially a similar type of load on the system. It's just more work for the system, but you can imagine a system where that would cause you to screw up in some way. All right. Okay, so I just want to cover these points real quick. Again, applications in most languages and the operating system can be covered by dtrace. And I think most importantly, the interactions between those. Going from, say, a low-level activity like writing data to disk or putting packets on the network up to your Java or Ruby or Node.js application and be able to bounce back and forth and look at those interactions. We can also trace those kernel interactions, which are very important for understanding low-level effects. When you're in a high-level language, the reason you're in a high-level language is so that you can do a lot with a little. The bad side of that, of course, is you can do a lot of unintended work with a very small number of lines of code. I'll give you an example. We were trying to help Twitter, this is back in their Ruby days in like 2006 or 2007, diagnose a problem. And we found a single line of code that was contributing to 20% of their CPU utilization in Ruby. And we made that small change and got a 20% win. So those kinds of things are common when you're in a high-level language. It can cause a bunch of unintended work in addition to intended work. All right, so that's dtrace. Now I want to get into the customer system. So now I'm going to talk a little bit about what this customer system looked like, what it was doing, and then walk through how we examined the system and give some general kind of perspective on performance analysis. Yes, sir, you had a question?
That was really cool. I'm missing something kind of fundamental. You probably already said it, but so from what I'm hearing, like all the kind of like OS utility people like university are sprinkling dtrace things in their code. Later, someone like me can exploit that. How did that happen?
So that's a great question. So the question was basically, where did these probes come from?
Yeah, and how do we add them ourselves?
Yeah. So, and I should have been clear on this point. You don't need to add them yourselves, and they don't necessarily. Not all of them were added by individuals. I'll go back to the terminal and give some examples here, if it lets me. There we go. So if we do dtrace minus L. FBT, minus N as well. This is the function boundary tracing provider. This finds every function entry and return everywhere in the kernel. Those are automatically generated. There's some cleverness in the way that we wrote that provider that identifies where all those functions are in the kernel. So we didn't need to walk through, like the folks at Apple, in this case, didn't need to go through every function and say, this is where it starts, this is where it ends, meticulously. Similarly, if I go to, no, I'm going to test fate here. What am I running? Safari. So if I pick like a Safari process, let's hope I picked a reasonable one, and I do PID that, and I list, oh, why did it fail to grab the guy? Let's try the high numbered process, maybe that's me. Nope. How about TweetDeck? So if I go to some process and I list all the probes in it, what dtrace is going to do is walk up to that process and start scraping through its symbol table to figure out where all the functions are. And this is kind of a painful operation. Well, let's hope my laptop comes back from it. Because there are going to be like potentially millions of different functions in this single process. What is it doing? Okay. I'm going to let that run for a bit. But so the answer to your question is there are both kinds of probes. There are dynamic probes, which the system figures out, like all of your Ruby function calls, all of your C function calls, all of your Node.js function calls. There are also static probes for known useful points of instrumentation, such as when I am putting a thread onto a CPU, or when I'm issuing an I/O to a device, or when a new thread is starting, things of that nature. Does that answer your question? Okay, great. I'm going to leave that running. We'll see if it comes back. But I'm kind of surprised that actually, let's try A.out. Man, no love. All right, we'll come back to that. And I'll let that run. Good. So, back to the customer system. So, wow, maybe I should not have let that running. So sometimes dtrace can have a large performance overhead if you're asking it to do something kind of stupid. I bet it's just allocating memory like crazy. I'm gonna leave that off, but we will do it at the end. Actually, let's do it to PowerPoint at the end and see how it likes that. All right. So talking about the customer system. So customer system is basically running an NFS server. It's an NFS server where they've provided some disks on the back end, some SAN fiber channel connected back end. And the clients are these weird AIX boxes running, I say weird in that like all AIX boxes are kind of weird in my opinion, running Oracle. It's moving about 300 megabytes a second. It's a 24 core system. The symptoms as described by the user are the way that these performance symptoms are often described. Latency is bad, our customers are angry. Rarely do you get very crisp definitions when people are talking about performance problems. Usually it's like, it sucks when X, Y, Z, or W. It's not like, my latency 2 sigma performance is exceeding the SLA, nothing like that. So the first thing I wanted to do, and I'm going to do this, I'm going to go and build up this script with folks so you can hang with me for measuring the NFS latency. So I want to point out these probes because I think they pertain to this gentleman's question over here. So in the kernel, there's an implementation of NFS. We could just use the probes associated with those function calls. I could open up a source browser and figure out what they are, but they've also specified some useful probes. Now, if you're not interested in NFS and kind of I'm losing your interest, imagine instead that this is Ceph, or imagine that this is your favorite database, and they've published probes that you can use to turn on and then measure certain things about the queries that you're executing. So in this case, we're going to start with the probes that pertain to writing and reading over NFS, and when the operation starts and when it completes. So then I'm just going to do the same thing I did in that little dtrace script. I'm going to say self points to TS equals timestamp. Again, TS is just a name I like to use, and timestamp is that nanosecond counter. And then I'll do the quantized based on the amount of time that's elapsed. Now I'm going to get a little fancier, and I'm going to say, if the probe is this write done probe, then I will insert a key into my aggregation that labels it. We'll see the output of this in a second. And now I want to get even fancier and say, I don't care just about read versus write, but I want to know about different types of them. There are cached reads versus uncached reads, like did I need to go to disk? Because obviously cached reads should be a lot faster, and maybe I want to separate out those two different populations. And there's synchronous writes versus async. Async can get returned immediately and so forth. So I'm going to get a little fancier and add a little snippet of code that helps me with that. And this is the script that I end up with, and I'll show you the output. All right. So now I go, I got even fancier, and I labeled my graph with microseconds. So now on the top, I have that ASCII art diagram, and below, I've got my Excel version to just try to clarify a little bit and also talk about log scale. So here, I'm measuring, in this case, this is cached reads. And on the left, we've got microseconds. We can see that most of the cached reads are in this normal distribution around 32 microseconds. Cached reads are fast, that's not surprising. On the left down here is a log scale on the x-axis. On the right over here is linear scale. This is really just to show you log scale is actually pretty useful. Linear scale smushes a lot of information and makes it hard to understand. So I look at this on the customer system, and it looks pretty good. Cached reads are not clearly a problem. Then we look at uncached reads, and we see kind of this bimodal distribution where there are a bunch that are super, super quick, like less than a millisecond, and then a bunch around 8 milliseconds. 8 to 10 to 20 milliseconds is not surprising. These are spinning disks. Probably that bimodal distribution is sometimes I hit out of the cache associated with that storage array, and sometimes I have to go to disk. Writes get a little more terrible. So now here I'm looking at asynchronous writes. And we've got 3 different populations. We've got ones that are super fast that probably hit some sort of non-volatile memory. We've got ones that are kind of speed of disks, kind of in the middle there, around 8 milliseconds, and then ones that are terrible. And for those who are a little tough at counting digits, the ones at the bottom correspond to 1 to 2 seconds. Okay, so this graph goes all the way from 64 microseconds for an individual write operation all the way to 2 seconds for an operation. And this is for synchronous writes. These are now for writes whose the client actually needs the response and needs it pretty quick. And we're seeing a similar, actually worse kind of trimodal distribution between those very quick ones, the kind of medium slow ones, and the incredibly terrible. So I want to stop for a second on this one, because this is already a huge, alarm bells were going off when we saw this. These are the kind of distributions that you might be, except if you're if you're looking at like natural phenomena. But when you're looking at a computer system that's supposed to respond in a certain amount of time, this is kind of the worst thing you could imagine. So again, we've got this population we have 13,000 that are less than a millisecond. We have 3,000 that are like 1 to 100 milliseconds, already getting pretty nasty, and then 200 that are a quarter of a second. It's tough to make a computer do something that takes more of a quarter of a second, especially and these are individual operations. So really, when you're making requests of systems, you value consistency over best time latency more than anything. I just want to take an aside. I'm sure folks have fallen into the same pitfall as I have, is focusing on averages. Everyone's talking about like average latency and so forth. Averages lie completely. In this case, the average didn't look so bad. It was actually around 30, 40 milliseconds. But the 99th or 95th percentile is just atrocious. It's in the order of nearly a second. Now I'm going to redraw that picture in a slightly different way. I'm going to take I'm basically going to take the value on the left, which is the duration, and multiply it by the count. And now I get a different picture, which shows the contribution of each of those buckets. And again, log scale on the left, and it shows that the time is dominated by those outliers. While there are many operations get satisfied in a very small amount of time, the biggest contributing factor is these outliers. Okay, so now, again, I've got an NFS server that's basically my product. It's talking on one end and delivering atrocious performance. But we've also got disks on the back end. So the other thing we need to assess in this processing system is how quickly are the back end disks responding. Because if they're responding poorly, then what can we do? Garbage in, garbage out. So first we look at reads, and we see pretty decent data, and actually that kind of matched what we saw with regard to the reads in the other slide. And then we look at writes, and we see also kind of fine data, and if anything, better data than you might expect. We've got writes that are a normal distribution around 2 to 4 milliseconds, and then again, normal distribution around this. So this is all by which to say the disks that we're relying on are fine. And the problem is clearly us. So unfortunately, we couldn't just say to the customer, well, it's your problem, not our problem. In this case, it really was our problem. Not that that would have flown, of course. But so now I want to talk about basic performance goals. I think when you're looking at a performance problem, there are two higher order bits here. One is get the idle out of the system. If the system is idle, or if there's work that could be done that's not being done, you have to understand that. You have to understand why. If you have a thread that should be busy and it's given up the CPU, or if you have a big queue of work that for some reason isn't getting scheduled, that's a huge problem. The other one, kind of paradoxically, is getting idle into the system. When you've got work that is being performed inefficiently, or when you're wasting cycles doing the wrong things, that means that the right things aren't getting done. So, those are the basic approaches that we took with this customer. So now I've got another dtrace script I'm going to share with you that I hope is comprehensible now that we've kind of done this dtrace 101 together. So we're using some of the same primitives that we looked at before. We say when a write starts, let's get a timestamp. Now we're using this neat static probe called off CPU. And unsurprising, it gets fired every time a thread is getting descheduled, is getting pushed off the CPU and then on CPU. Okay, so this shows us, this lets us measure how long we're getting kicked off the CPU for. And then we're doing one of these quantize operations. And the key here is that we're looking at the stack. So this shows us in the application, in the program, where we're getting kicked off the CPU and which of those stack traces is the biggest contributor. So I got this and I had thousands of lines of output or whatever, but the biggest contributing factor was this thing. So this let me see that I ran this for like 10 minutes and I saw that there was one point in particular that was kicking me off the CPU for anywhere from 1 to like 15 seconds. So I've got a thread that really wants to do work and it's being told no for 15 seconds. This is obviously a huge contributing factor to these outliers. And I'll talk about what the stack means in a second. Now I'm going to give a quick overview of how ZFS processes data. And it's actually kind of neat. So there are 3 batches of data. There's the open one where you're kind of filling it up, all the data is flowing in. There's the quiesced one, where data is kind of ready to be written out to disk. And then the syncing one, where data is actively being pushed out to disk. Originally, when we shipped ZFS, there was no size limit. So what would happen immediately is if the disks couldn't keep up with the application, we would fill up all of memory. So the application would blithely start writing as fast as it wanted to. We would start finding everywhere we could to like put the little pieces of data it was sending. The disks couldn't keep up, and eventually the system would roll over. So then we needed to implement some sort of back pressure. And I've seen a bunch of talks at this conference that actually are basically on this topic, on throttling requests from customer systems, and where whether it's billions of IoT type devices that are sending telemetry. I saw a talk yesterday from a gentleman from Comcast who wanted to rate limit requests coming in from set-top boxes. Similar types of concepts where you need to apply back pressure to the folks who are generating the information in the requests. So back to this picture, which I showed you earlier. The rate throttle that we implemented was really deeply stupid. So basically it would say, how much data should we accumulate? And the answer we came up with was, of course, 5 seconds worth. Why 5 seconds? It's a good amount. So, and then the question is, well, how many megabytes are 5 seconds worth? And so we wrote this terrible piece of software that tried to evaluate, based on previous experience, how much data you could write over 5 seconds. And I looked at this, I used dtrace and evaluated on the system, and that would fluctuate everywhere from 50 megabytes to a gigabyte. So this kind of agent in ZFS would make wildly different assessments. And as a result of basically not being able to anticipate this, we kept on guessing wrong. We would think 100 megabytes and that's it, and then tell everyone to stop, or they'd say gigabyte and that's it and tell everyone to stop, again, with nasty consequences. But another thing I want to mention is that and this is important for when you're writing any kind of rate limiting device. Originally, ZFS was written with the idea that a single vendor would control the ZFS software and the full system. But now when let's say you're operating in a customer environment where the customer is providing you with storage, or the customer is providing you with a backing store of some kind, whether it's a disk or a storage array or a database. Your software probably wants to treat that backing store nicely. It wants to make sure it's not overwhelming that backing store, not overwhelming that system. The mistake we made was that you actually do want to overwhelm it a little, and I'll tell you for the following reason. So if I go back to that slide where we saw write performance, what we realized is that we were getting write throttled, that the backing store was not able to keep up. So we went to the storage team, and we said, your storage is not performing well. And they looked at this data, and they said, looks good to me. And so we were being very sensitive to the backing store and not creating a problem there by design. But what we realized is that for these customer systems where you have potentially different types of politics, has anyone worked at kind of a large organization? Yeah, and large organizations kind of measured by finger pointing, not by the number of people. Like, you're in a large organization. Like, my family of the three of us is kind of a large organization at times. But you're in a large organization when something goes wrong and people start pointing fingers. And when we started pointing our fingers at the storage team, they didn't care for it. So what we actually need to do is create a small amount of pain so that they could share that pain with us, rather than isolating them from that pain. So what we started doing is cranking up the queue depth. At first we said, we'll only send you 10 requests at a time, and that's probably enough. And we started turning that up more and more. And now this is the latency distribution that we saw as we cranked it from 10 to 32 to 64 to 128. And you can see that that peak goes from about 4 milliseconds to 16 to about 32 milliseconds, and then all the way out to 65 milliseconds. At which time, the storage group absolutely agreed that they were in a tremendous amount of pain, and the overall performance, the overall throughput of the system started going down. So again, there's this sweet spot of both sharing pain so that you can get some collaborators to help you and accept that there actually is a problem that they could help you with. But then also kind of pushing enough load on some of those backing systems where latency is going to get worse, but you want to tune it to the point where throughput doesn't start to go down. All right. So that's kind of the first thing we looked at is there's work to be done. Why is it not getting done? And this is one of the reasons. The next technique that we looked at was profiling. And I'm sure folks have done a lot of profiling. dtrace is a good generic profiler. I can go back to this if it'll let me. And let's make this a little wider. And, why are you not letting me? I can just do dtrace minus n, dtrace minus n, profile 199. And I can look at just do a timer-based profile of what executables are running at a given time. And that's going to fire 199 times a second. I can choose whatever frequency I want. And it'll show me, these are the applications that are actually active. And I can dive in even a little deeper than that. So profiling the system lets you understand the other side of the question is, when I'm busy, is that work important? You can either do broad, kind of timer-based, sampling-based profiling, or you can do a more focused type of profiling. In this case, we did a little of each. We looked at timer-based profiling, and we also looked at particularly noisy functions, and then looked at the functions that they were calling to get that contribution. So in this case, just for context, our expectation of the way we designed the system was for that. So this is all functions that function SPA sync calls. Our expectation was that DSL pool sync would be like 99% of the activity. So this unaccounted for 20% was something we had completely not anticipated. This is work that we thought was basically not important given the criticality of where this was in the processing. So that's another area that we focused. The next, and this is a little related to profiling, is lock contention. Has anyone diagnosed a lock contention problem? Yeah, okay, a couple of folks. Are folks familiar with what lock contention is? A couple of nods. I'll assume that some of those, there's at least one of those non-nods that means you don't know. It means when you have two locks or you have two threads that are both trying to acquire the same lock, one wins and the other one waits. And the amount of time that thread needs to wait can potentially be a huge problem. Now, In this case, in the implementation of locks that we were looking at, there's kind of an interesting thing where if I have a lock, or if I'm a thread and I try to get a lock, and I notice that some other thread already has that lock, and I notice that that thread is already on CPU, rather than putting myself to sleep, which can be really expensive, I'm going to spin, with the idea that in a well-written program, locks should not be held for a long amount of time. So, my time is better spent maybe spinning for a couple of nanoseconds and then noticing that the lock. So it's the right kind of orientation as long as your threads are all holding the locks for a short amount of time. In this case, and this is nanoseconds, you can see there are outliers here as long as 67 milliseconds. So this computer is having a terrible day, and I've got one guy who's just hanging out in a tight spin loop on one core for 67 milliseconds at a time. And so this one lock identified here accounted for 24% of all of my CPU time on the system. Okay, just atrocious. This is probably the hottest lock I've ever seen. Okay, so getting to some of the ending, and I don't have time to go into detail about each of these pathologies, but again, we had algorithmic problems associated with the right throttle, which we ended up completely rewriting. That's a different talk that I would also love to give at some point, potentially on less short notice. We removed a bunch of inefficiencies in the code. A bunch of the code was doing this really entertaining thing where it would have these long linked lists, and it would basically take all of the nodes from here and put them over here. Just kind of like it's like, instead of just taking the deck of cards and moving it, it would like deal. It would like take each card and deal it across. And it would do a little bit of manipulation along the way. But we thought, well, what if we just shift the pointer over there? So we were able to remove, in particular, that unaccounted for 5 to 10 to 20%. And then we broke up the hot lock. I wanted to point out here also that in blue, you have our trimodal distribution that I was talking about before. You have, and after we wrote the new right throttle, we had a nice single-moded distribution while still improving the overall latency. Okay. So lessons learned here. One of the most important ones is that when your customer is having a bad day, telling them to do something that doesn't work is terrible. I started running our support organization shortly after this, and we had kind of a 3 strikes you're out policy, with the idea that if you tell a customer to go try something, by the 3rd time, they're just gonna assume you have no idea what you're talking about. Even if it's like good preventative care, even if it's kind of an obvious thing, well, it's like your shoelace isn't tied, why don't you just go tie it? Even if it's really good advice, like that burns a strike. So, and the way that you can be more and more certain about your remedy is to collect data to fuel that. Another big mistake that I neglected to mention is that we spent a bunch of time looking at what the customer thought was a reproduction of the problem. If you're looking at a performance problem, look at the performance problem. Don't look at what the customer thinks is load generation. In this case, and I kind of wish this wasn't screened, but I hope the customer doesn't see it, we noticed finally after a kind of a week that we were looking at synthetic data that the actual load wasn't running. We said, well, why isn't the load running? They said, don't worry, it's a load generator, and it's written in C, just like Oracle. So we think the load is pretty similar. And it's one of these moments when you're like, how do I even respond to that? The mere fact that it's written in the same language is going to have a totally different I/O pattern, and it will do vastly different things. So don't look at, whenever possible, don't try to reproduce it, don't look at synthetic data. And that's why it's so important to have your system for doing diagnosis, data collection, and evaluation in situ on that box. So the right tools let you ask the right questions. Take as many turns as possible. I showed you just a couple of explorations, but I've got about 20,000 lines of text that I captured from these sessions to gather data, to be able to explore one hypothesis, back out, explore another, and that's so important for the diagnostic process. And then, of course, always be magnanimous with the customer, even when you solve all of those problems. Thank you very much. So in addition to this being up against Rust in production, and thank you for choosing this over that, I know that we've got lunch right after this, but if folks want to hang out and ask some questions, we've got a microphone there. So
How does dtrace compare to Sysdig?
yeah, so I talked to Loris. So folks heard the question. I talked to Loris over at Sysdig. He actually sent me a very nice note when he first started, or when he first shipped Sysdig. And Sysdig, for folks who don't know, is kind of I would describe it, and I hope Loris wouldn't be offended by this, as a system call performance tool that looks like it's written by the folks who wrote Wireshark, because it is. So it takes the philosophy of collect up every system call that's happened on your single box or in your cluster, and then do like kind of packet analysis based on that. So Sysdig also has some really whizzy stuff that's like, you can write little Lua programs to do your visualizations on top of it. I think that dtrace and Sysdig are pretty different, but again, similarly for performance analysis. Sysdig is focused, I think, still exclusively on system calls, although my expectation was that was going to change. I don't think it's designed to, again, it takes the kind of fire hose approach of collect all the data and then figure it out later, which is very different than what dtrace tries to do. But then dtrace doesn't have some of the more advanced kind of processing and visualization. So I think and I actually, in a workspace, I have like the dtrace data generation for Sysdig visualization. That's kind of one of my half-baked, not really working projects, but it's totally possible in theory. So kind of complementary, related in terms of inspiration. Other questions? Yeah?
So for those that are trying to crack the egg, still like learning dtrace,
Yeah.
like there's a barrier to entry, and
Yeah.
I find that mentoring is a little easier. Like, what's your suggestion?
So question was, I think, basically, how do I learn dtrace? I think that there are a couple of presentations out there. One I wrote, if you Google like dtrace bootcamp, I think is still pretty good, walks through a bunch of examples. I find that for most tools, I can read as much as I want to, but until I'm actually ready to use it in anger, I don't actually learn it. So I think part of that is kind of having that discipline to know, like, okay, I know I'm having a bad day. I know that the customer is screaming at me, but what I should do is take this opportunity to learn a new tool. Brendan Gregg, a former colleague of mine who's now at Netflix doing some great performance work, also has a big collection of dtrace scripts that he ships that make it a lot easier. He's written a great book about it. There's a bunch of dtrace examples just out there generally. There's starting to even be Stack Overflow populated with dtrace scripts on particular topics or for particular languages. And then I feel like I'm bringing up Perl a lot, but I feel like it's a lot like Perl in that you might like flip through the Camel book, or I guess like click through it on your Kindle or something, or maybe you don't look at books anymore. But you find an example that almost does what you want, and then you kind of tweak a little bit, and I think that that's a pretty common case. But again, start from the places you know, which is start from tools you know like TOP or PRStat or MPStat or things that give you a good systemic look, or start with your language-specific tool, whatever you use to understand the performance or functionality of your Ruby program, your Java program, or whatever.
Trust.
Everyone loves trust. Everyone loves trust. Was there a question over here? Yeah. Or Sysdig even. You can start from Sysdig and use that to dive in and say, now I see all these system calls. What are they doing? Why are they doing it? And drive me to the line of code. So again, complementary tools. Yes, sir.
I just wanted to see what your take was for Linux and dtrace.
So dtrace exists on a couple of different variants of Linux. Oracle has written a port of dtrace for Linux, which started out terrible. Like, it caused data corruption and it was kind of made me really angry. But now it seems to be working. And then there are a couple of other folks who there are ports available. I don't think it's in any of the main distros, but I don't really know. Other questions? Awesome. Thanks so much.